Hello there, everyone. Welcome to episode number 692 of this here electronic engineering podcast called Amelia's Weekly Fish Fry, brought to you by eejournal.com and written, produced, and hosted by yours truly, Amelia Dalton. Today, I'm joined by Dr. Maha Achour, CEO and founder of Kodamai. Maha and I are diving into the shifting landscape of AI, moving beyond the cloud and centralized data centers toward a more distributed agentic future. We discuss why governance must travel with AI agents, what it means for trust to be architectural rather than procedural, and how Kodamai's math-first approach is helping engineers build verified AI systems that can thrive in the real world. So, without further ado, please welcome Maha to Fish Fry. Hi, Maha. Thank you so much for joining me.
Thank you for having me.
Absolutely. Okay, so Maha, for years we've thought about AI as something that lives in the cloud or inside a centralized data center. But now AI is becoming increasingly distributed. So, what's driving this shift? And how does it change the way we design intelligent systems?
Very good. So let's understand, and I'll cover this question in three parts. The first point, how did we get here? And the answer is very simple. If you really look at history, the Socrates cooperative method, how he used to bring people, at that time there were no machines, no computers, just human brain, right? So think about a distributed human brain. He'll bring a bunch of people and ask them just to converse, ask questions, challenge them each other. So this is the argumentative dialogue used to stimulate this critical thinking, and that's how he learned in the absence of machine. So now you really want to think about the power of the human brain. Humans. I just want to make sure that the audience understand the human factor is always going to remain so powerful along this path. And then being a particle theoretical physicist, I always appreciated how pure math was able to discover and understand the micro and the macro world decades before machines verified them experimentally. So I just wanted to learn that language when I did my PhD at MIT. And ironically, my first publication in 1989 was just quoted in the cover page of Science magazine, using this mathematical method to understand the physical network of the neurons in the brain. So it tells you an elegant and simple and powerful math can really play a big role, augmented by human brains, to understand this intelligent factor. Now, over time, thanks, of course, to the internet, thanks to all these compute power that have been distributed in data centers and in servers, data was generated by human again and by industries. So this is where we are today. Large language models started being trained on these data and operating completely in the core. And then, of course, over time, the intelligence started to become distributed because it had to be accessible in real time. It has to also be processed in real time. This is where the edge and the client side became also very critical. What is so disruptive, in my opinion, is the agentic factor now. Is now we're migrating from just pure data and models into processes, regardless if this is an enterprise process, if this is a robotic process, autonomous vehicle process. Now processes are being placing this data distribution, and this is where the agentic orchestration at scale is so critical. And this is where we're heading. So that's my point three, heading into this agentic orchestration at scales. And it has to have a built-in governance and correctness in order to be deployed properly in these organizations.
So, Maha, as AI agents move out of the field and begin making decisions closer to where the data is generated, governance becomes much more complicated. So, why is it important that governance travels with the agent rather than remaining in a centralized location?
Okay, excellent questions. And I can answer it in two ways. I can go into the deep math of Kodamai, but I believe most of your audience won't understand it. But I can give an example. And a perfect example is the semiconductor industry. I've also designed some of these RF chips over time, so I understand that process. Think about today's chip development from the excruciating design and development phase and testing processes, taking into consideration the precision, the compliance, the IP, the design governance to basically deliver the final chip that targets this quality assurance and meets all the audit requirements. It's a very complicated and very expensive process, right? Now think about that mechanism that exists today, if you fast forward decades from now, where now you have a nanoscale compositional building blocks. Think about these nanoscale building blocks instead of these just layered wafers and very expensive processes. And these building blocks, they have these interfaces, these type smart interfaces. They know how to position themselves, how to compose the final chip based on the input requirement or input clear instructions from the engineers. That will really transform the governance that we have in the semiconductor industry, design and development and production, into a built-in fabric at the nanoscale fabric where the governance and the audit mechanism is built into these compositional building blocks with their type smart interface. That's exactly what we are targeting for the software agentic orchestration, where governance and trust and these audit trails are built into the fabric of the orchestrator instead of like today's semiconductor. You build the agents and then you test them and then you verify them and then you pray they don't make any errors.
So, Maha, we also need to talk about trust. We're hearing more people say that trust must be architectural rather than procedural. So, what does that mean in practice? And how can engineers build trust directly into AI systems from the ground up?
Perfect question. And that builds up on what I just mentioned in that example of this nanoscale fabric. If you take a look at today's workforce, the enterprise workforce, they operate in as much coherent way, follow the procedure, and try to be as trustworthy as possible. Agents need to follow the same process, but agents are built by engineers or by AI using just these very straightforward codes and augmented by tools or by other algorithms. But as we transition from this old, decades old data ontology, and that's where the disconnect is happening with today's AI agents. Because all what they do, they take the data, they augment it with the tools and the processes, and they create the agents. But there is an underlying shift. We're transitioning from this decades-old data ontology into organizing the whole enterprise process. So the problem today is not in this brute force methods based on the data and tools, building these LLM agents or reinforcement learning agents, but how do you scale them? How do you get these agents to collaborate, to make decisions at the edge, or even if they propagate to the client side with a pure correctness? And for this, you need this agentic underlying fabric that turns business into code instead of just writing functions or classes into software. And to do this, we developed, so Kodamai developed the Calvin Grove platform. In its heart, it turns business engineering into software engineering, where now workflows become first-class citizen, composable. Remember the composable factor when I mentioned this nanoscale fabric for the semiconductor, future fabrication, this composable micro element where they can check all these artifacts, they can prevent errors from propagating, and emphasize how these composable nature, where this process structure now lives in a purely mathematical world of types. And types is kind of well known to software engineers in very low level implementation codes. But if you go to the formal method in computer science, types, they have a much more impactful application. And this is where our types interfaces. So now you have the composable modules that basically build those agents. The agents are built on these composable modules, and these composable are interconnected with these typed interfaces. We call them contracts. Now we have a whole class of runtime errors that rules out any errors before they can even be executed. This is where correctness by instruction, by construction is basically developed. And this is where trust is basically built into the system instead of bolted on top of the system. Now, as you know, today we inherited a hardware and an infrastructure driven by industrial revolution. Everything you see today, including the data centers, came from decades-old industrial revolution where human muscles were replaced by machines. Now we're entering the intelligence revolution, where the human brains are going to be augmented by these software running across all tiers. But that disconnect between the old hardware and the new software needs to also transition. That is the new paradigm. That is the real new paradigm that's going to drive AI to AGI and ASI over time. I'm very excited about being at the forefront of this with our Calvin Grove language. And hopefully we will be able to have an impact on both the software today and the hardware in the future.
Looking to the future, how do you see distributed AI, embedded governance, and architectural trust reshaping the relationship between hardware, software, and autonomous agents? And what should engineers be doing today to prepare for that future?
Absolutely. That's a very good question. And I was just at UCSD a few weeks ago, and the moderator asked exactly the same questions because the audience, the engineers were eager to understand. And that goes back to what I just said, is that there should be a shift into the academic world in educating these engineers, not only on the old-fashioned hardware and engineering system that we inherited over the decade, and also empower these engineers and enable them to think outside the box, how this new AI revolution that we are witnessing today in software impact the engineering from material science, from semiconductor production, from various governance in design and development. Now, going back to the tiered structure, how does the governance and trust propagate, or how does it really is implemented in this agentic orchestration as we go, across all tiers? And I'll give a very perfect example, the autonomous vehicle as an example, because, they are robots and they are operating, with very little human in the loop. So if you really think about the autonomous vehicle, it can operate independently at the edge, independently from the client side, in the ego vehicle, independently from the edge, independently from the core. And it has to operate in a very safe way, which means that trust and governance needs to be completely met. And for this, the old-fashioned way of doing this process was just collecting data, training the sensor fusion, and covering all corner cases. Now there is a shift into embedding generative AI, into embedding reinforcement learning, embedding this agentic orchestration mechanism into the vehicle itself to make sure that the safety and also the governance is met at all time, independently of the connectivity with the infrastructure and connectivity with the core. Now, when these vehicles are also connected to the infrastructure via V2X, or V2V, for example, you are in a more distributed fashion. And now, how do you get this distributed infrastructure propagating and implemented and also enforced? So having this underlying fabric that basically interconnects these agents across these various tiered level is very important. This way, you do not impose governance after the fact, after the car crashed. No, you impose the governance in building into the system. And that fabric needs to be present both in the software and in the hardware. And that's exactly what Calvin Grove compositional modules with these typed interfaces are basically enabling.
That makes sense. Now, Maha, given Kodamai's focus on AI agent platforms, how does your approach specifically address the embedded governance and architectural trust challenges we talked about, particularly when agents are operating in distributed edge environments?
Very good questions. And here I'll go a little bit into some technical terms that your audience will also understand. So Calvin Grove, both the language and the platform, the orchestration platform, the agentic orchestration platform at scale is based on a distributed, typed microservices framework. So here are some very loaded description: distributed, typed, and microservices. And the daemon in Calvin Grove acts as a hypervisor for systems of agents, where now we have a class of meta agents. These are privilege level agents above all the other agents. You have the managers, you have the executors, you have the collaborators and decision maker agents and so forth. But you have the meta agent that sits at this privilege level above all the agents where they can manage them. And the daemon basically is this special kind of network hypervisor where at every single component, even if it's run remotely, without that connectivity in principle, is implemented in that language, and it has these correctness in the typed interface where things basically propagate and where things actually are prevented to propagate when these mathematical typed interfaces don't match during that propagation. So for that matter, all the Calvin Grove built-in infrastructure is basically uses this typing discipline, and it is maintained across all tiers. Again, we go back to the fabric notion instead of this distinctive today that exists across the three tiers: the core, the edge, and the client side, and each one is basically running its own show. So basically, its daemon is the one that is responsible for that. It enforces it at every single boundary of the network.
So, Maha, we're looking at a unique situation between capital infrastructure and academia. So, Maha, how can we bridge that gap and how can we empower the next generation of engineers?
So, there will be a shift, and the shift is going to happen very gradual. So what do students do, and what does the industry need to do to bridge that during that transition? Because universities are basically stuck. The curriculum is still the old-fashioned way, governed by this industrial revolution, while they are adjusting it and updating it and getting into the intelligence revolution era. There should be a transitional period. And what I really think should work, these industrial companies, especially the one with very intense capital, because the AI capital is concentrated in very few private and public sector, they need to tap into the students' bodies in these universities and work with them directly to make sure that the master thesis, the PhD thesis they're working on are in line with what they are trying to do in the future, instead of just having the professors imposing these very old-fashioned topics that basically are going to go nowhere post-graduation. So I highly encourage universities, the industry, and the student body to work together in the next 10 years to make sure this transition happens smoothly.
Okay, so let's also talk about Kodamai's math-first approach to agentic AI. Can you explain what that looks like in practice, especially for creating verified interfaces and auditable decisions in complex engineering systems?
Yes, that's honestly probably for this you need to get my CTO or my CSO to talk about this because it's a very abstract level of math. But let me simplify it to your audience. Let me start with the types. Your audience understand what types is because when they program, they have to define the type of that variable. Is it a text? Is it an integer? Is it a complex number or so forth? So data are basically typed in these C++ or Python code and so forth. Now, when you talk about the typed interface, which also implies typed agents, it's a completely new, different notions. And you cannot really even visualize it using the code that people are using today. So this is where the abstract math happen. Now, types is basically resides in a new formal mathematical methods in computer science called category theory. Now, what does that mean, category theory? So we have the types, right? We understand what types are. Now let's understand what categories are. Now, if you go to LLM and you look at the history of, from ChatGPT to where we are today. Lots of various ways, mathematical approaches to understand and optimize and improve on what these large language models are doing and visualize them in using geometry, hypergraph, using very in different ways to understand them. But if you really look at these nodes and how these nodes are connected across these layers, you will realize that there are some redundancy, there are some paths that causes propagation to converge, and that becomes a very big problem. And this is where people start thinking about how do you simplify these very complex systems that they've been working with. And they start putting these multidimensional understanding of that problem. So think about category theory as a connection, as various elements or various steps that needs to be followed. And how do you connect these steps? What do you do first? What do you do next? And what do you do in between? And if you take a look at it from a very abstract way, those methods and those steps and those elements can look exactly the same across various disciplines. Like if you are cooking, for example, you have a recipe, you have the ingredients, you have the process how to do that. And you can actually visualize it into a paragraph. And if you do the same thing into how do you want to solve a problem in physics, you also have the same graph, and they may look exactly the same. So this is what category theory is. It's basically those very high level of processes, they may look exactly the same, but it's in the type system into how do you implement them where the differentiation happens. So that's basically what Kelvin growth is driven by this categorical framework of these formal methods augmented with these type interfaces and type system. But at the same time, also, we augment the LLM and the machine learning portion with neurosymbolic to improve the intelligent part of this implementation.
Fantastic. Well, Maha, before I let you go, it's time for your off-the-cuff question. So, if you could have one meal right now, it doesn't matter if it's on the other side of the world, you need a passport to get there, what would you have?
Oh, wow. I love Vietnamese cuisine. I love the French fusion Vietnamese cuisine. I don't know all the names, but that would be my meal.
Nice. That sounds wonderful. Well, Maha, I think that's all I have time for today. Thank you so much for joining me.
Thank you.
Well, folks, that's all I've got for this week's Fish Fry. If you'd like more information about Kodamai, I've included a couple links below the player on this week's Fish Fryin' page on eejournal.com and in the description for this week's YouTube episode as well. Hey, have you checked out EE Journal on social media yet? Well, you should. You can find us at facebook.com/eejournal. If LinkedIn is your thing, I dig it. You can follow us or me on LinkedIn, and we are also on Blue Sky Social and Mastodon as well. And we have a YouTube channel, youtube.com/eejournal. Folks, it is chock full of all kinds of techie videos, including our very popular Chalk Talk webcast series, hosted by me. And of course, you can subscribe to our EE Journal YouTube channel as well. Thank you, everyone, for tuning in. If you know of any cool new technology or heck, you just want to chat, shoot me a line at Amelia, that's AMELIA, at eejournal.com, or post a comment on our forums on EE Journal. For the week of July 31st, 2026, I'm Amelia Dalton, and you've been fried.